Hello everybody, and welcome to the continuation of exercise 1. We are looking at page 99 here. Hopefully by now you've given an attempt at all of these problems, tried to answer these questions on your own. In this video, we're just going to work together through a couple of these, okay? And the rest of them you can look at the written solutions and check your answers that way. Okay, and the ones that I'd like to look at are the very last two, okay, starting with part E down here. Okay, so this introduces an interesting type of a ring. Okay, so first there's some new notation to get used to. So z adjoined the square root of 2, that's the way that that's read in words. That's going to be the set of all things that have this form. A plus b times the square root of 2, where a and b are integers. Okay, and turns out that that's a ring. One can show that that's a ring under just ordinary real number addition and multiplication. Okay, and we'd like to go down this list and just see what properties this has. Okay, so first of all, is this a commutative ring? Well, it is, because everything in that ring is just an ordinary real number, and we know that real number multiplication is commutative. Okay, is there a unity element in that ring? There actually is. Okay, I claim that 1 is the unity element. How do we know that 1 lives in that ring? Well, it lives there because it fits the form. Remember, everything that lives in the ring has to look like this. And we can write 1 as 1 plus 0 times the square root of 2. Okay, and so that's in our set. Okay, and we know that the real number 1 acts as a unity element. You take that and multiply it by anything, you're going to get the same thing back again. Okay, so 1 is our unity. Okay, and then what about the question of zero divisors? Okay, are there any zero divisors in this ring? And again, zero divisors are non-zero numbers that you can multiply together that would give you 0. Okay, I claim that there aren't any. Okay, I'm going to give you a reason here and see what you think of it. Okay, no zero divisors. Okay, because this ring, z adjoined the square root of 2, is a subring of R, and R has no zero divisors. Okay, so the claim that I'm making here is that the fact that we have a bigger ring R that we know has no zero divisors, and it implies that this smaller subring inside of R can also not have zero divisors. I'd like you to think about that, okay, and convince yourself that that logic makes sense there. Okay, and so what about the question of integral domain then? Okay, is z adjoined the square root of 2 an integral domain? Well, it's got to have 3 properties. It's got to be commutative, it's got to have a unity, and it's not allowed to have zero divisors. Notice that we have all 3 of those properties. Okay, and so therefore the answer has to be yes. Z adjoined the square root of 2 is an integral domain. Okay, and does it have any units? Okay, well, one unit that it has to have is the unity element. Okay, it has a unity element, so 1 is on that list. And -1 is also in that set. We can write -1 as -1 plus 0 square root of 2, so that's in our set. Okay, what's interesting though is that there are actually other units that you might not expect that live in this ring. Okay, so for example, 1 plus the square root of 2 is actually a unit in this ring. Let me see if I can convince you of that. Okay, so to do that, to convince you of that, I would have to demonstrate that we can take 1 plus the square root of 2 and multiply it by something that's in our ring that would give us the unity element back. And it turns out that what works is -1 plus the square root of 2. Notice that that exists in this ring. It fits the form. And let's do that calculation and just see what happens, what we get if we do that. So we're just going to FOIL here. -1 plus the square root of 2 minus the square root of 2, and then plus 2. Notice if you do the algebra there, you get 2 minus 1, which is 1. That's the unity element. Okay, and there may be other units in here. To be honest, I don't know. Okay, that's a little curiosity. Maybe somebody has figured out a complete list of what the units are, but I point that out just to demonstrate sometimes unusual things can turn out to be units in rings like this. You might play with this a little bit and see if you can find other examples that work. Okay, and the last one I'd like to work together here is part F. Okay, so this time we're talking about the direct sum of, or actually I think our book uses the term direct product, sorry. So z plus z. So remember that, again, that's the ring of ordered pairs where the coordinates, the elements in each coordinate are integers. Okay, and our operations are going to be component-wise integer addition and multiplication. We're going to see if we can answer all of these questions. Okay, so is this a commutative ring? Yeah, it's got to be commutative because we're talking about the integers in both coordinates. Okay, and we know that multiplication is commutative in the integers. Okay, does there exist a unity element in this ring? Okay, something that we could multiply anything by and get that same element back. Okay, answer to that is also yes. Okay, so we can take 1, 1. I claim that that's the unity, and just to illustrate that, okay, why does that work? Well, observe that if you take 1, 1 and multiply it by any mn, okay, remember our operations are component-wise multiplication here. We're just going to get mn back again. That's the definition of what we mean by a unity element. Okay, now we come to the most interesting question, I think. Does this ring have any zero divisors? Okay, well, at first glance, you might look at that and say no, because of the fact that we know that z by itself doesn't have any zero divisors, but we have to be a little careful here. It actually does have zero divisors. Okay, let me see if I can convince you of that. Okay, so for example, notice that if you take 1, 0 and multiply it by 0, 1, do that component-wise, you get 0, 0. Okay, and the thing to emphasize here is that 0, 0, that's the zero element in our ring, and notice that these two elements are non-zero. Okay, if you make any one of the coordinates not 0, then you're talking about an element in the ring that's not equal to the 0 element. Okay, so those two elements are zero divisors. Okay, so this is true even though 1, 0 is not equal to our 0 element and 0, 1 is not equal to our 0 element. Okay, so they're zero divisors. All right, what does that say about whether or not we have an integral domain? Well, integral domains don't have any zero divisors, so by figuring out that we have zero divisors, we've shown that this is not an integral domain. Okay, and if you think about this a little bit, you can kind of play this same game with any product of two rings. You can find zero divisors in this way. Okay. And then the question of units. I'm going to go ahead and list the units in this ring and let you think about why these are the only ones. Okay, so our unity element is going to be a unit. 1 and negative 1. Okay, if we multiply that by itself, we're going to get the unity element, so that's a unit. Negative 1, 1. And then finally, negative 1, negative 1. Okay, those are the 4 units in this ring.